This demo explains Apache Kafka and shows a tiny Clickstream pipeline running locally on my computer. I'll start Kafka in KRaft single node mode, create a topic, run a Python producer that sends JSON click events, and run a Python consumer that reads and aggregates them. Kafka requires Java on the machine. If this, so we first install Java 17 or higher. So now we need to download Kafka locally on our computer. For that, we run the following commands. First, we change our directory to the home directory to keep the Kafka files there. After that, we set the variables, that is the Kafka version and the Scala version variables, so commands are easier and reproducible. After that, we run the curl command, which downloads the Kafka tarball from the Apache archive into my home directory. The downloaded file is the binary distribution of Kafka. After that, we extract the tarball. The extracted folder contains the Kafka binaries, scripts, and default configuration files that we will use. After that, we change to the working directory for the Kafka. So downloading and extracting the Kafka binary gives us the command line tools that will be used to run the local broker and manage the topics. So now we run these commands, which creates a minimal server properties for KRaft mode that runs Kafka without Zookeeper. It makes this a single process that acts both as a controller and the broker. We run these commands because KRaft mode requires initializing or formatting the metadata storage with a cluster ID. The first command generates a random cluster ID and stores it in the cluster ID variable. Now I am starting the Kafka broker using the Kafka server start script and the KRaft server properties we created. The broker will output startup logs and you'll see messages confirming listeners bound to ports 9092 and 9093. So now we'll make a directory to run our demo project and open VS Code in this directory. In VS Code, we set up a virtual environment and make a requirements.txt file that lists the Python dependency kafka-python, the client library we use to connect to Kafka. We then make four files. The first one is producer.py. It's a small script that connects to Kafka and sends JSON click events to the demo clicks topic. Here, the user and pages arrays are simple sample data for randomized events. The make event function builds a single event dictionary, a page, and a timestamp as milliseconds since epoch. Then we make consumer.py. This file subscribes to the demo clicks topic and prints each message while maintaining a simple in-memory page view count. Then we make aggregator.py. So this script demonstrates a continuously running stream processor. It runs a background consumer thread that updates a share count library dictionary, while foreground printer function periodically prints the aggregated snapshot. This pattern mimics a real stream processing job that consumes messages at scale and periodically emits metrics or updates to a downstream system. Now I have created a topic named demo clicks using the Kafka topics. This partitions argument means the topic will have three partitions. These are independent ordered logs that allow parallelism. The replication factor 1 means no replicas because we are on a single broker. So now we will start the consumer file that is subscribed to the demo clicks topic and is configured to read from the beginning so that we can see all the events as they arrive. We set up the virtual environment and start this file. The consumer prints each message it receives, showing the partition and the offset. The offset is the message sequential position within that partition. So now we start the aggregator. It will print the aggregated page view counts every 2 seconds. This illustrates a simple continuous stream processing job. After this, we'll run the producer to send 30 simulated click events to the demo clicks topic. Each send prints which partition and offset the broker assigned. You can see the consumer receiving the same events in the real time and aggregator updating counts. Observe that messages with the same user key go to the same partition. This preserves per user ordering. Because the producer prints partition and offset, you can see how messages are located within a partition's log. So under the hood, Kafka stores messages in append-only segment files per partition and disk. Each message gets an offset, an integer that acts as its unique identifier within that partition. Consumers track offsets to remember where they left off. The broker handles writes efficiently by batching and appending to files and letting OS level input-output handle disk flushes. In multi-broker clusters, partitions have leaders and replicas. Leaders accept writes and followers replicate the partition data for fault tolerance.